Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Thomas Wenisch from Carnegie Mellon University. Thomas is finishing up his PhD this year. He's one of Babak Falsafi's students. Thomas has done some work in statistical sampling methods for simulation. He's developed the SMART system and the simplex simulation infrastructure. He's not going to talk about that today. Instead, he's going to talk about his thesis work, which is on prefetching for shared memory multiprocessors. Thomas.
Okay. Thanks a lot for the introduction, Owner. So as Owner said, I'm Tom Wenisch from Carnegie Mellon University. And today I'm going to tell you guys about temporal memory streaming. Temporal memory streaming is a hardware approach to try to reduce the average memory access latency observed by load instructions. And in particular, we've designed temporal memory streaming to address the data structures and access patterns of commercial server applications, things like online transaction processing and web serving applications, which exhibit particularly poor memory system performance on modern computer hardware. So let's begin by talking a little bit about why memory accesses have become such an important bottleneck in the design of computer systems. Okay? So this graph here shows the relative performance of processors and memory over the last 2 decades or so. And if we go back to about 1986, an instruction and a memory access took roughly the same amount of time. And now for 2 decades, processor performance has been improving at somewhere between 20 and 50% per year. And over that same 2-decade period, memory access latency has only improved at about 7% a year. Okay? So why is this the case? Well, in processors, we've had a huge acceleration in clock frequency from generation to generation. And architects have come up with ever more clever microarchitectures that increase the amount of instruction level parallelism that this hardware can extract from the program. So technology scaling has really driven processor performance improvement. But in memory technology, DRAM designers have really focused on improving density rather than access latency. And so as we stand here today in 2007, one main memory access takes the same amount of time as 500 non-memory instructions. So the goal in this research is to try to figure out how we can reduce the enormous stalls that these programs exhibit waiting for data to show up from main memory. So clearly, this is not a new problem. We've known that there's a memory wall and that processor and memory have been diverging in performance for quite some time. So let's begin by talking a little bit about the conventional approaches that computer architects employ to try to bridge this processor memory performance gap. So I'm going to talk about 2 conventional approaches that are used in absolutely every processor today, or every modern high-performance processor today. So the first approach to avoiding long latency main memory accesses is to actually avoid accessing main memory at all. What we do is between the processor and main memory, we add a hierarchy of caches on the chip. And the reasoning behind this is that the smaller we make a memory structure and the closer we place it to the processor, the faster we'll be able to access it. So a 64 kilobyte level 1 cache that's right next to the CPU might be only 2 clock cycles away, while our tens of gigabytes of main memory are more than 200 clock cycles away. And this idea works because applications tend to reuse data, right? Once I access some piece of data and bring it up to the highest level cache, it's very likely that I'm going to access that piece of data again in the near future. Architects call that idea temporal locality. Right? So this is great, right? Temporal locality is going to save us. Moore's law is still giving us transistors, so why don't we continue just expanding this cache hierarchy, adding more levels or more transistors to every cache? Well, there's really 2 problems with that approach. So first of all, we're getting diminishing locality returns on each of these transistors that we're adding to the processor's cache hierarchy. Most of the temporal locality that these applications exhibit is captured in the first few megabytes of cache. And so as I keep adding yet another level here, I'm getting I need to add exponentially more cache to get kind of that same performance improvement that I got from the previous levels of the cache. And now, secondly, if I add a second processor to this system, and there's some piece of data in that processor's cache, and the first processor wants to access or modify that piece of data, now, even if I add an unbounded amount of cache to each of these processors, I'm not going to be able to reduce the communication latency between these things. Okay? So caching doesn't help us with read-write shared data in multi-chip multiprocessors. Okay. So what else have computer architects tried to do to reduce main memory access latency? Well, the second conventional approach that every modern high-performance processor employs is to try to hide memory latency with useful work. And this is exactly what out-of-order execution does. So rather than trying to interpret all of the instructions in the program in the order that they occur, what out-of-order execution does is kind of build a small data flow graph over some limited window of instructions, and then interpret instructions in data flow order. So rather than computing for a while, reaching a memory access and sitting still while that instruction accesses memory, and then computing for a while again, the out-of-order processor will issue that memory access earlier, as soon as it can calculate the address that will be accessed. And now we're overlapping some of this memory stall with useful work. So again, this is great, right? Why don't we just keep making the out-of-order instruction window bigger until we get to the point where this entire red stall is fully overlapped by useful work? Well, again, there are two problems with that approach. First of all, there are many structures in a modern processor that scale very poorly with the size of this instruction window. They scale quadratically or worse. And so it's very difficult to make a piece of hardware that can actually find more work and memory stalls to overlap. And secondly, this entire approach depends on the fact that these instructions are independent, right? If the instructions and the memory accesses depend on one another, out-of-order execution doesn't help us at all. We need to interpret all those instructions in order to calculate the addresses. Okay. So I told you at the beginning of this talk that things are particularly bad for commercial server applications like online transaction processing. So let's look a little bit at the characteristics of those applications which really confound these conventional approaches. So I'm going to make the claim that server applications really do defy these two approaches to hiding main memory latency. So first of all, these applications depend very heavily on shared data structures, a lot of read-write sharing. So even with an unbounded amount of cache, we're going to have communication traffic between the processors. And secondly, these applications depend very heavily on linked data structures, things like B-trees, linked lists, and so on. And because these data structures are built out of pointers, they lead to many dependent sequences of memory accesses. And so now, out-of-order processing can't help us issue all those memory accesses in parallel. So the net effect of these facts is that on modern computer systems, these applications spend 1/2 to 2/3 of execution time stalled waiting for values to come from main memory. And this is a result that's been shown over and over again in the research community. So
is it worse now?
I don't think it's gotten worse because the acceleration of clock speed has slowed down. So we're not getting 50% a year anymore. We're getting something less than 20% a year. However, it's not getting better either because memory really isn't accelerating either. And so now these two things are kind of keeping pace.
20 is a whole lot bigger than 7 still.
That's right. I mean, I'm not going to make the claim that it's getting worse. That's unclear, but it's not getting better.
Well,
So
if it's not getting better, I'd just be surprised if it hasn't gotten worse.
We are observing that it's getting worse.
Okay.
okay. So great. I mean, that only helps my point. But in any event, we're already at the point where it's 1/2 to 2/3 of time. And so in this talk, I'm going to talk about the read portion of this stall time. I have some new work that's going to be presented later this year at the International Symposium on Computer Architecture that talks about how we can avoid the write stalls that these applications have in the multiprocessor environment. So our goal is to figure out how to get from this picture of how execution looks today to something that looks like this, where we can fetch data earlier and in parallel in order to try to overlap as many of these memory stalls as possible. So how can we go about doing that? Well, one approach, rather than those two conventional approaches I talked about, is to try to predict where memory accesses are going. So let's predict future accesses. And this is exactly what hardware prefetching approaches do. Hardware prefetchers examine the memory accesses issued by a program and try to deduce some kind of pattern in the way the program is accessing memory, and then based on that extracted pattern, guess which address is going to be accessed next and request it early. Okay? So this is great. This is exactly what we want to do. Now, the problem with the existing prefetchers that you have, for example, in Core 2 Duo or in Pentium 4 or the latest AMD chips, is that these prefetchers depend on very simple patterns in the memory access sequence, in particular, strided patterns. So on a processor today, if a program accesses A plus 2 and then A plus 4, the existing prefetchers will be able to figure out, oh, we're going to A plus 6, A plus 8, and so on. But this doesn't help us with pointer chasing data structures, right? Where these are truly random, potentially, addresses in memory that are linked together and that we follow in sequence. And now there certainly has been quite a bit of work in the research community on prefetching approaches, dependence-based prefetching approaches that try to guess that something is a pointer and chase down these chains. But most of this research has really not looked specifically at what's going on in server applications to try to come up with a mechanism that can predict the sophisticated traversals that we see in something like online transaction processing. So the approach that we've taken in our project at Carnegie Mellon, which my thesis is a part of, we call spatio-temporal memory streaming. Okay? And the key observation here is that memory accesses repeat along two dimensions, along the space dimension and along the time dimension. Okay? And so what I mean when I say that memory accesses repeat along the space dimension, if we look at the layout of memory accesses, relative kind of the space of memory pages, we actually see the same pattern of accesses over and over again. For example, this picture here might be a picture of accesses to a database page, where we initially access the page header, and then we go to, for example, the tuple slot index at the bottom of the page that indicates where records are located. And then we access certain fields within fixed-size records that are spread over the page. And now as we visit an entire table, we'll see that same access pattern on page after page of memory. And now, in the time dimension, what we find is that data structures that are built out of pointers get traversed in the same way over and over again. So for example, if I see some traversal that starts with the accesses Q, W, and E, and I later traverse that same data structure, I'll again see that traversal with addresses Q, W, and E. So the idea in this approach is to try to observe these patterns in space and time, in hardware or in software, and when we see that a pattern is going to repeat, predict the rest of the traversal and bring that data near the CPU ahead of the processor's explicit requests. So within the context of this project, my dissertation work focuses on the temporal aspect, so temporal memory streaming. And so the most succinct way of summarizing this idea of temporal memory streaming is hardware records and replays recurring miss sequences. Okay? So where does this help us? So let's imagine that we have a sequence of pointers, A points to B, points to C. Okay? In a baseline processor, when we execute a sequence of code that traverses this data structure, we'll issue a load for A, and then the processor will stall for a while. And then when A returns, it can calculate the address for B and then issue that, and so on. And so we have all these serial delays on a main memory access. With temporal memory streaming, if we've already observed this access sequence A, B, C, when we see the access to A, we're going to predict the remainder of this access sequence, and now we can fetch all of these addresses in parallel. Okay? And so now we've broken this fundamental serial dependence chain that was inherent in the way the data structure was being accessed.
To be clear, A, B, and C are specific addresses.
That's correct.
Program abstraction, it's not a variable name, it's
an address. I mean, so from the hardware point of view, it's a cache block address.
Cache, right,
but
sure.
That's right. This whole streaming mechanism with the temporal stuff is tied to specific addresses.
Okay.
We're going to observe specific traversals repeating.
Okay.
So we're going to get three advantages from trying to do this approach. So first of all, we're going to be able to fetch data in advance, right? We're fetching B and C before we actually discover the instruction that wants to load those addresses. We can fetch in parallel, even if the underlying access sequence is fundamentally a dependent access sequence. And finally, we can take advantage of the fact that we know the order of the accesses in this traversal. What that's going to let us do is use a flow control mechanism that delivers the data onto the chip into a small buffer just before it's needed. So we can do things like avoid polluting out and displacing other useful data and still have this data arrive just in time. And so just to give you a preview of what I'm going to show you in the evaluation, I'll show you that we get 6 to 21% performance improvement on commercial web processing and online transaction processing applications in a multiprocessor context. So let me give you an outline for what I'm going to cover today. So first I'm going to begin with some motivating observations that underlie the way we've designed this temporal memory streaming mechanism. Then I'm going to characterize for you a bit what these MIST sequences look like in these commercial applications. I'll talk about the implementation of temporal memory streaming, and then finally I'll discuss some of my ongoing and future research interests, potentially here at Microsoft. So let's begin with the most important observation that really is underlying this whole idea of temporal memory streaming. And that is this, that MIST sequences repeat. Okay? So why should we believe that MIST sequences repeat? Well, it's because code and data structure traversals repeat. So if at some point in program execution we see a traversal over data structure and we see misses to A, B, C, D, E, and so on, if later in the execution we see an access to location A, it's very likely that that access will be followed by the remainder of that traversal, B, C, D, E, and so on. And so we call this property of groups of addresses, that they tend to be accessed together, temporal address correlation. Okay? And there's been quite a bit of evidence in the literature that there are relationships across addresses in memory access sequences and traversals. So for example, Joseph and Lai showed that there was pairwise correlation, that one address would suggest a very high probability for some specific successor address. And Luck generalized that relationship to accesses that were not immediately adjacent in time. So this access here suggests that some specific address will be accessed several accesses later. And Chalimby showed that we can actually find sequences of accesses that repeat if we look at the accesses to the L1 cache, so the loads and stores issued by the program. I'd also like to draw a contrast between this notion, temporal address correlation, and the traditional notion of temporal locality. Temporal locality is a property of a single data element, that when I see it, I'm likely to see it again in the near future. Temporal correlation is a relationship over groups of addresses, that they tend to be accessed together. Okay. So throughout my talk, I'm going to use this term stream. And what I mean by a stream is an ordered sequence of memory addresses. So the second key observation that underlies our design for temporal memory streaming is that there's temporal locality in the streams that a program visits. Okay? And why is this the case? Well, because the working set, the data structures that you work with have some temporal locality. I work with one data structure for a while at some point in a computation, and then I work with another data structure. And in particular, in the multiprocessor environment, what we see is that there's often repetition in access sequences across CPUs. So for example, suppose these addresses are all locks. At some point in a computation, CPU 1 might acquire all these locks A through E, and then at some point in the near future, CPU 2 is doing a similar kind of transaction or computation, and it needs that same set of locks in the same order. And so we'll see these repetitions across nodes. So we call this idea temporal stream locality. So it's suggesting recent streams are likely to repeat. And if we think about the converse of that idea, it means that more distant streams, so things that we observed longer ago in the past, are less likely to repeat. Okay? And it's that observation that motivates us to try to track these streams at runtime, because the freshest stream information is most likely to give us benefit in trying to eliminate future accesses. And so this is why we choose to try to track streams at runtime rather than statically or periodically instrumenting a program to try to identify these sequences. So with these underlying observations, let's turn now to talk a little bit about what streams look like in these commercial applications. In particular, the question that's really most important to answer is how much repetition is there? What is the opportunity to try to eliminate main memory accesses with this idea of repetitive MIST sequences? So in order to try to approach that question, what we're looking for is repetition in memory access sequences. And finding repetition is actually pretty much the same thing that data compression algorithms do, right? Data compression algorithms are locating repetition in some arbitrary sequence. And so to try to get an upper bound and quantify how much repetition there is, we've analyzed memory traces using a data compression algorithm in order to let the data compression algorithm find these long repetitive sequences. And in particular, we're using the sequitur hierarchical data compression algorithm. And actually, there's good precedent for using this particular algorithm. It was actually Jim Laris, who's now here, who was the first person to suggest the use of this particular compression algorithm for analyzing repetition. And Trishul Chalimbi, who's also here, actually also used the same approach to identify hot data streams in the L1 access sequence. And so sequitur is a very useful algorithm because it constructs a grammar to summarize the repetition that there is in some input string. So this string here, we as humans, these might represent misaddresses. We as humans can see that ABC occurs 3 times and ABCD occurs twice. What the sequitur algorithm will do is construct a grammar which, if fully expanded, regenerates that input sequence. But the key observation here is that these non-terminal symbols, the production rules in this grammar, correspond exactly to the repeating streams that we're trying to identify. And so we can construct this grammar and then walk a representation of this grammar in order to count kind of how much repetition is there, how long are these streams, where do they come from, and so on. So we're going to take this analysis approach and apply it to programs in order to get kind of a quantification of our opportunity. So let's take a look at the results of this analysis. So let's begin with this most important question, how much repetition is there? So what I'm showing you here on the vertical axis is the fraction of all of the main memory access, so all of the misses out of the last level of cache in a multiprocessor environment. So there's these commercial applications here running on 16 processor system, distributed shared memory system. And there's 8 megabytes of local cache per processor, which is a little larger than we have in most systems today. And we've actually chosen this particular size deliberately because that is the size where Oracle in particular has really captured kind of its first major level of temporal locality. So just a little bit more than 4 megabytes is what Oracle needs to capture that primary working set. And so now we're really looking at the point where continuing to increase the cache size is bringing us diminishing returns. So there's 2 bars here for each of the applications. The blue bar considers the case where we can observe a repetition on one of the processors in the system and then later on see that same stream on another processor, whereas the red bar restricts repetition just to a single processing node. So it has to be observed and then the repetition has to happen on the same processor. I've also hashed out on each of these bars a small portion at the top. That represents the first miss on each of these sequences. And as we'll discuss later, I'm excluding that from the opportunity here because we're going to use that miss as the trigger event to actually cause this streaming mechanism to go and try to fetch the data. So that's not really opportunity.
Is this just D cache or D and I both?
Just D. We're just looking at data access here, right? We're not looking for streams in the instruction access sequence.
Maybe you should.
So that's an interesting point. So I would say one of the things that you'd have to do there is potentially separate out instruction and data into separate recording mechanisms because while data access sequences, logically, you can understand why one thread will have kind of a repeating sequence of data accesses. It's not obvious to me that the instruction misses are going to happen in the same interleaving with respect to the data accesses.
I agree. You should probably separate them,
but there should be repetition. That's correct.
I would think there'd be more in the iStream.
Well, what we're asking there in the end is how repetitive is the control flow, and how whether we can do better than a branch predictor, for example, is trying to figure out where the program's going to go. One part of it is with this cache size here, with 8 megabytes of cache, a shared L2 cache, the number of instruction cache misses that go to main memory is very small. There's an awful lot of L1 misses, and so it's a very interesting question, can I move things from the larger, slower cache into the L1 cache? Because that actually will affect performance for instruction misses. But off-chip, the number is relatively small. Things fit pretty well.
Is that really true for DB2 and Oracle type applications?
At this size. So again, that's part of the reason why 4 megabytes is the magic number. Or 4 megabytes is the magic number where the number of instruction misses kind of also stops dropping off.
So what you said there was for instructions is probably not interesting because there's not much opportunity left after the instruction, after the iCache. So here, the way I should read this opportunity on the data side is I might be able to, for example, in the Apache case, reclaim 50%
of all the main memory
of the misses.
That's correct.
Of which, and the misses are responsible for some other smaller fraction of the total time.
That's correct, and we'll get to all of that. I'll show you the results on what fraction of time are spent on these things. But you're absolutely right. Right. This is we have to multiply this by the amount of time that already matters. And the other thing you have to realize is that not all of these misses are necessarily costing us the same in terms of time, because there's already some inherent parallelism, right? We're going to analyze this in the context of an extremely aggressive out-of-order processor that maximally does what out-of-order processing does, and then ask how much can we get from this approach.
So if you use the same graph, if you produce the same graph for the instruction side, it might look similar. The problem is that there's a very big constant on the outside that says there's not that much opportunity all
for the off-chip misses. That's correct. But there would be a substantial. So I can tell you for a fact that these particular applications, these two right here, spend about 13 or 14% of their time in our environment on L1 iCache misses that are serviced by the L2 cache. And so there's a 14% time where you might be able to recover it, but there are some other complexities with trying to do this on the chip. Well, I think it'll become clearer, kind of what the difficulties are a little bit later. So there are really 2 points that I want you guys to take away from this particular slide. And so the first one we've already mentioned. If you look at the blue bars, more than half of the misses, the main memory accesses in these applications, are in fact part of some repetitive sequence. And the second key point here is if you look at the red and the blue bars, there's clearly a lot more opportunity if we can take advantage of accesses that happen on one node than are seen on another. And the reason that that's true for these workloads is that with this cache size, in fact, communication misses, so coherence activity between the nodes, in fact dominates the overall off-chip memory accesses because they share data so heavily in places like the operating system and the database metadata, things like locks and so on. So we'll talk some more about that as well. Question?
How dependent are these numbers to your transaction mixes? What kind of transactions are going
That's a good question. So we've done this with the TPC, TPC-C workload over here, which has pre-specified transaction misses. I would suspect that on the whole, the transaction mix isn't going to change things largely because most of what we're getting is from metadata as opposed to from like leaf stuff. So it doesn't. What matters is the transaction needs locks, and the thread scheduler has to kind of figure out which thread to run. In a uniprocessor environment, this stuff might look a little different. On the web transaction side, we can talk some more afterwards. I have data on where this stuff is coming from, and it might be useful at the end of the talk to look at some of that. Might clarify that a bit more. Another question.
And just to get an intuition, maybe I missed this, but what is the length of such a stream that you're typically talking about?
Beautiful question, because that leads me right to stream length.
I wasn't paid for the question.
No, that was outstanding timing. So now I'm going to show you kind of a cumulative distribution of the stream lengths. And now 100% on this graph represents the top of the blue bars from the previous graph. So this is just the subset of misses that are part of some repetitive sequence of length at least 2. Okay? And the most important point to see when looking at this graph is that many of these streams are actually quite long. So the median length is on the order of 10 cache blocks. And if we look in particular at the web servers, there are some streams here that are hundreds of cache blocks long. And occasionally, even though they're not particularly large fraction of overall misses, there are streams that are thousands of misses, where you're repeating exactly the same access sequence as some prior point in the program for 1,000 consecutive accesses. So what does this say to us? What it says is that we can't just grab an entire sequence the moment that we predict it and dump it into the cache hierarchy. Because a sequence of something like 100 cache blocks, it's extremely likely that if we go and fetch 100 cache blocks, we're going to displace other useful data from the cache hierarchy, right? So this, but we really would like to take advantage of all of the opportunity that these long streams provide. And so this is why we try to use a flow control mechanism, where we try to stay just ahead of the processor in this access sequence and bring the data onto the chip a little bit at a time into a small buffer. And, one second. I'd like to contrast our approach here with depth prefetching approaches. So there have been a number of prior prefetchers that try to go several misses ahead of the processor. Ours is really the first approach that wants to go, take advantage of this entire sequence as opposed to just take, every fifth miss, incur a miss latency. Question?
So once you've got flow control, it seems like I don't understand why you want a special buffer on the side. Why not? Once you're not going to blow out your L1 cache, why not just use the existing memory you have, the existing fetching schemes that you have, and just dump it into that L1 cache?
We'll talk a little bit more about that, but the short version is that it turns out that this prediction mechanism that we're using either gets exactly the right stream. We manage to say, address A tells us exactly what the processor is going to do. And so you follow that stream and you deliver it at this buffer and it's perfect, right? And the flow control is easy and we might as well have been putting it in the L1 cache. Or address A has absolutely nothing to do with what comes after it. And now, if we go and fetch that sequence, it's useless. Okay, we would just do nothing but displace useful data. And by putting this in a buffer as opposed to in the cache hierarchy, now it doesn't cost us. It only costs us bandwidth. It doesn't cost us pollution when we go and fetch some of these blocks that are in fact erroneous. Okay.
What's the cache line width you're using?
It's 64 bytes here, which probably wouldn't drastically change things, but
it's worth it.
One more question before we move on.
So I have a question about the algorithm you mentioned a few slides ago.
Okay.
If you have streams of very different lengths, right, can go up to thousands or some are much shorter. I mean, this algorithm seems to be like decomposing this kind of string into.
Well, so what it'll do is it'll give a grammar rule which in its expansion uses 2 other grammar rules. And so when I did the stream length analysis, I'm categorizing things into the longest repetition that is discovered by the algorithm. And those are not guaranteed to be the maximal length repetitions in the entire input sequence. There are algorithms that will do that. Sequitur is a linear time, online thing. So
it's like being a complicated algorithm. So
that's correct. I'm not going to implement that in hardware.
Okay.
This algorithm is really just an analysis tool for us to ask the question, how long are the sequences? How many are there? What should we be doing? Okay. We'll now talk some more about what we actually do. Actually, again, you're leading me right to where I'm going. Quick question?
Yeah, quick. So, does this include the uniprocessor streams? Or is there a difference between uniprocessor
this is
streams?
based off the blue bars, which would allow repetition either from you or from someone else. So,
is there a difference in terms of the length between those two?
I don't think that there is. I don't think that we would visually see a difference. It's just this 100% would be, represent a much smaller fraction of the overall misses. But I have looked at that, and as I recall, there was no qualitative difference in the shape of this curve. Actually, it might bias a little bit towards the longer sequences. Sometimes these short repetitive sequences are things like 4 locks that get grabbed in a row, in particular in the web servers. So you might see this tail in the web server applications get heavier, and because kind of this part became less important. But yeah, to first order, it wouldn't really be different. So one more question, and then let's get on to the implementation.
Here the median is 10 instructions. Now,
10 cache blocks that are accessed.
10 cache blocks. Now if you weight it by how much money you make, like you care more, how far does that move it? What's it?
So you're saying relative to
if
the
you weight
length.
1,000 block cycle, 100 times more than 10 block cycle, where does the median move?
So what we lose, which we'll also discuss at length, is we're going to lose some of the performance gains we could have gotten on the very short sequences because it takes us some time to do this lookup, which will also become clear now. So the longer sequences benefit us more, but once it's about beyond a length of 6 or 8, we've gotten to the point where we're probably going to be able to exploit all of the benefit, and now it doesn't really matter. Longer is just better because you avoid more misses. So let's talk now about how can we actually implement this in a system. So we're going to implement this in the context of a hardware distributed shared memory machine. So let's talk a little bit about what that is. In a distributed shared memory system, what we have is each processor node has some associated cache, okay, and a portion of a global shared memory space. And these nodes are connected through some interconnection network that allows any CPU to access a memory location in any of the memories, including those that are located at another node. And in order to facilitate keeping track of where the latest value of a memory location is and which nodes have copies of a memory location, there's a directory at each node which knows either a processor currently owns a particular cache block or several processors currently have copies of a cache block. And this directory mechanism is used to facilitate coherence, keeping one global value as memory is modified. So this is an interesting system for us to try to implement this temporal memory streaming idea because we can take advantage of some of the existing mechanisms in the distributed shared memory machine to implement some of the mechanisms we require to do TMS. In particular, this directory provides us a mapping from all of the cache blocks in the system to meta information, so we can add our lookup information that we're going to need to find streams to the directory. And we can piggyback the bookkeeping traffic from TMS on top of the existing messages that are needed to maintain cache coherence in this system. So in the next slide sequence, I'm going to show you the 3 major steps of temporal memory streaming on these time diagrams here. So time is going down. And there's 3 nodes involved in this process. So node 1 is going to observe a missequence, and node 2 is then going to try to take advantage of that recorded missequence. And the directory node here is the node that's responsible for keeping track of what's going on with address A. Okay? So the first step in temporal memory streaming is the record step, right? So node 1 has some sequence of misses, A, B, C, D. It's going to record the address sequence somewhere in local memory at node 1. Okay? At a later point in time, node 2 is going to incur a miss to address A. And now, in accordance with the regular coherence mechanism in this distributed shared memory system, it will send a request to the directory asking for the latest value of address A, and the directory will either provide that value or redirect the request to whichever node currently has the updated value for address A. Now, in addition to these regular responsibilities, in TMS, we're going to give the directory a new responsibility. The directory is going to know in that same data structure that tracks addresses that node 1 was the last node to observe address A. And now it's going to send node 1 a message to locate A in its miss sequence. Okay? Node 1 will then read out that address sequence from main memory and forward the list of addresses B, C, and D to node 2. Okay? And now, once that address list arrives at node 2 will then issue requests, normal prefetch requests, like a software prefetcher, for B, C, and D in parallel. Okay? And then these addresses will return, and subsequent accesses at node 2 will turn into local hits on chip instead of potentially remote misses. And if node 2 continues to repeat this access sequence that was observed at node 1 and node 2 will continue to communicate so that node 2 could potentially follow this history of misses at node 1 without bound. So let's dive into each of these 3 steps, record, locate, and stream, in a little bit more detail and talk about the hardware that we need to add to the system in order to implement each of these steps.
Tom,
Sure.
did you do analysis on the misprediction part of the streams, in the sense that when we identified the streams of A, B, C, D, what are the cases where only A is observed, B, C, D is observed in X% of those cases?
So we definitely have looked at statistics and also come up with mechanisms to try to reduce the distance that will follow something that's wrong, or to avoid following down things that repeat. What I have not looked at specifically is trying to tie that back to what's going on in the software. We've tried to tie the streams to things that are going on in the software, but we haven't tied the mispredictions.
SIGWare itself only finds the longest parts, and it wouldn't actually necessarily raise a red flag saying that, I also see a whole bunch of A's all by themselves without the C, B, C, D following them.
So we've done some analysis to look at, for example, for addresses where there are multiple successors. This certainly exists. And one of the things we've asked is, what are the heuristics you should use to choose among multiple options when you have an address and there are multiple options? And it turns out, guided by this principle of temporal stream locality, using the most recent occurrence of A, in fact, is the best simple predictor for which among the various historic occurrences of A tells you what is happening next. So there might be more sophisticated things that we could do, but in terms of things that don't drastically increase the amount of state you need and so on, just going with the most recent is the best. And we've also come up with some tricks to try to reduce how often we'll erroneously follow a stream by comparing 2 prior occurrences. So we don't just look at the last occurrence of A, we look at 2 previous occurrences of A. Okay, if they were followed by the same thing the last 2 times I saw it, well, that drastically increases the probability it's going to be the same thing this time. And the point of divergence tells me where to stop. When they are different, now we'll be more conservative. We'll wait maybe for one more access before we decide which way to go. So another quick question.
Do you only look at one misaddress to trigger the next set of prefetches?
Yes.
Or is there a benefit? So is there mispredictions due to just looking at that, or would it be more accurate if you looked at 2 misaddresses?
You could use diagrams. Yeah. It does. What it does is it reduces coverage, because you lose cases where, for example, there's kind of you would have gotten part of the sequence right, even though you would have gotten the very next miss wrong. So and it also costs you the coverage on that very next miss, and potentially makes the next guy even later. But it does increase accuracy in the sense that you're even less likely to fetch things erroneously. So in this environment, because bandwidth is fairly abundant, because these workloads are missing all the time, they're using a few percent of the available memory bandwidth in these kinds of systems, because these kinds of systems are really designed for scientific applications that use way more bandwidth. So we're talking about 3% of the bandwidth that the database is using by itself. So we can be somewhat wasteful with bandwidth, so it's better to be aggressive. But yeah, there might be situations where that's not sensible.
The only downside of the bandwidth wasting, it's not the bandwidth wasting, it actually is the cache coherency problems. Because all these guys now start to grab these things.
That's true.
And they will start to fight within each other to try to say, no, I need explicit access to that.
One of the things that's really important is you want to have a system that's going to hide store latency, which we do talk about, like I said, in ISCA 2007 this year. You could make things worse if you can't avoid waiting for a store when you take a permission miss. So it's very important in any kind of more aggressive prefetching scheme.
Okay.
One more question, and then I should move on. Go ahead.
You say that you can waste some bandwidth because these machines are designed for scientific applications. I think the guys who want to make money on the database will buy machines that are designed for database applications.
Yeah, I mean, so it's kind of odd. I mean,
available at CMU.
Again, you design a machine for more than one workload, and in online transaction processing, you're always going to use less bandwidth because you're doing more pointer chasing than even data mining type applications, right, where there's a lot of parallelism. So I don't foresee the situation changing that for the specific workloads we're looking at here, there will always be available bandwidth, right? And you're correct that bandwidth comes from the application of money, right? The more we pay, the more bandwidth we get, almost without bound, not quite, but so it's still a good trade-off for these kinds of workloads. So let's talk briefly about each of these 3 steps in just slightly more detail. What do we have to do for them? I'll present some evaluation results, and then I still want to spend at least 5 minutes or so talking about future work. So the first step is record. And so the key observation here is we're trying to record sequences over this entire huge address space, all these data structures that are accessed. And since the data set is very large, our storage requirement is proportional to this data set. We can't possibly store this sequence history on chip. So instead, we do it in main memory. This structure called the cache misorder buffer, so that's a private part of local memory. At each node, we probably need some cooperation from the operating system to arrange to have this private region of physical memory. When we get a fill, in addition to providing the data to the cache, we'll record in this large circular buffer that miss address. And so basically, what this circular buffer is maintaining is the history of the last several 100,000 misses in one giant sequence. So there's no delineation of where sequence boundaries are in this thing. It's just, again, based on this temporal stream locality idea, we have all of the most recent sequences somewhere as subsequences of this giant history. Okay? And now, of course, the problem is how do we do the lookup? How do we locate a particular sequence within this history when we have some subsequent miss? So the key idea here, again, is to keep this mapping from addresses to where they have previously been recorded in the directory. So in the directory, we'll store both the node and the location within that node circular buffer where an address has been recorded. Okay, so for all addresses, whenever there's an append to one of these circular buffers, as part of the memory traffic for actually performing the miss that led to that append, we'll update this recorded location in the directory. So the directory will know on some subsequent miss to A, okay, not only is A shared, so you have to go to the directory anyway just to service the miss for A, you'll also find out, aha, node 1 last incurred a miss to A, and it recorded it at location 57 in this misorder buffer. So now I'll send a message to node 1 asking it to look at location 57 and find what happens next. So then the third step is the stream step. Okay, so now we want to, the idea here is to take advantage of this ordering property so that we can fetch data to match the rate at which the processor is going to consume it. Okay, so we have a sequence of addresses that arrives. Okay, we'll put that in some kind of queue, and now we'll fetch data from that queue into this buffer on the side next to L1, avoids the pollution issue, and we can keep up with the CPU by setting a high watermark in this buffer. We want to be, 8 blocks ahead, for example, in the sequence. And so every time the processor accesses a block, we'll go and get the next block off the FIFO and issue the prefetch. And so there's this natural rate matching between the rate at which the processor consumes things and the rate at which they get replaced into this streamed value buffer. Okay. So let's talk a little bit about the valuation of this idea. Yep, sure.
Since you're doing it from L1 cache, are you using physical addresses or?
We do use the physical addresses here, and we're running one application, even though it's many threads. So if the threads had different virtual memory mappings, that might be useful. So yeah, we're not dealing, for example, with the TLB and the translations here. You'd still have to incur a TLB miss so you could find this address that has now been moved onto the chip and is sitting here in this buffer. So all of our analysis is with physical memory.
I might be missing something, but my recollection of, and it's been 20 years since I studied this, my recollection of the way that the directories work is that they're associative lookup tables, right? That are based on the physical addresses that you're mapping.
Okay.
Not proportional in size to physical memory, they're proportional in size to the caches. Right.
That varies. So there are some systems so in some systems you need to track, even if a block is invalid, track the state of that block. And so depending on what we're assuming here is a full map directory, which is not one of these things that, so what you're basically paying is probably a 3 or 4% overhead over your entire physical memory to have 20 bits roughly on the side. And now I'm doubling that. So it's another 3%. So the question is, are we better off dedicating yet another 3% to have this lookup structure versus using that 3%, for example, to expand the buffer pool? And you're going to get 20% improvement here. You're not going to get 20% from 3% more buffer pool. Right? So it's a good trade-off. But you're right, the expense is high. And one of the things that's kind of the last details that I'm working on in my thesis is finding lookup mechanisms. I mean, obviously, most of the space is completely useless, right? There's only a small number of... it's a large fraction, but it's still a fraction of the addresses for which this lookup information matters. Let's be smarter about it, right? So let's talk about evaluation briefly, and hopefully we'll still have some time to talk about some future work. So we evaluate this using a full system out-of-order timing simulator. So the key feature here is we can look at Oracle and DB2 running on Solaris. And this particular measurement instrument is extremely slow, something like 1,000,000 times slower than the hardware that it represents. So we have a very small budget to actually explore these programs in terms of the number of instructions we can run. So back in ISCA 2003, I presented a simulation methodology that uses statistical sampling, so simple random sampling on these workloads, to reduce simulation time to something reasonable while still giving us some quantification that, in fact, what we've measured represents the entire workload. The one thing I'd like to say about the processor here is that this is a very aggressive processor that we don't know how to build today. So we're kind of trying to maximally beat on the parallelism that's already there. That won't be improvement for our technique. We're only going to get improvement in cases where it really is a pointer chasing type thing where the out-of-order core can't help. Or, for example, run-ahead execution by itself would not be able to get it. Right? So let's look at the results. I'm going to show you the evaluation in 3 steps. So again, on this graph, 100% is all of the off-chip misses in this 16 CPU system with 8 megabytes in the last level of cache at each node. The first blue bars here consider what we eliminate if we ignore timing. So if all operations in the system are instantaneous, memory access are instantaneous, stream movement is instantaneous. The question that we're trying to answer here is, this simplified lookup, just looking up to the most recent occurrence, how well does that perform relative to what the compression study says is out there in terms of repetitiveness? So we've chosen some scientific applications here that have repetitive misaccess sequences that can't be gotten by a stride predictor. So of course, because of that, they're 100% repetitive in terms of the memory access sequence that we see. And now on the commercial applications, the important thing to see here in the blue graphs is that the top of these bars are roughly the same as what I showed you with the compression study earlier. So we are, in fact, capturing the opportunity, ignoring timeliness effects that the compression study suggests is available. Okay? So now, the red bar and yellow bars look at this in an environment where we do consider timing. Okay? And the key observation here is, since we're going off chip to look up these repetitive sequences, this lookup latency is similar to the main memory access latency. Right? So we're not just going to lose that first trigger event, but also potentially the next event on the sequence while we're trying to find this stream. And so what this shows you is, the overall loss shows you things that, in fact, we were too late. We were completely, the processor had already issued the request. And the yellow shows you where we only made a partial improvement. We hit part of the latency. We issued the request before the processor got there, but then the processor did have to wait. The bottom line, however, is that this mechanism is getting about 3/4 of what the compression study, even considering timeliness, suggests we should be able to get. So that's pretty good. So now let's turn that into performance impact. As we were discussing earlier, we have to multiply these coverages times how much time was being spent on these off-chip reads in the first place. Okay? So for each application here, I have two bars, a baseline system that doesn't include our approach, and the system with temporal memory streaming, normalized to represent the same amount of work. The important part of the bar here is the red part of the bar. That's what we can address with this approach. And again, you can see in some cases, despite huge accuracy, for example in Ocean, perfectly repetitive miss sequence, 100% accurate. And yet the performance improvement is very small. And the reason is that Ocean is close to bandwidth bound and does have parallel accesses. It's not a sequence of dependent misses, and so the gain is very small. However, we still get significant gains in these commercial applications. So this here shows speed up. It's the same data, just represented differently with the confidence intervals that we got from our sampling approach. And the bottom line for the commercial applications is that we get a 6 to 21% performance improvement, which certainly 21% is very worthwhile for a large-scale commercial database running on a multi-million-dollar server. So let me just summarize, and then hopefully we can still spend, I'll take 1 or 2 short questions on this, then I'd like to talk for 5 or 10 minutes, if we can go over by 5 minutes, on future work, and then, of course, I'll take as many questions until you guys decide that you guys are sick of hearing from me. So if you remember one thing from this talk, remember this. Main memory accesses cost hundreds of cycles, okay, and that's a problem that we have to worry about and have to do something about. And if you remember 2 things from this talk, then remember that our solution is temporal memory streaming. So the key idea here is record and replay recurring miss sequences. And this is exactly what we want to do when we're trying to break this pointer chasing dependence. And so you can see here the impact varies, but it's certainly worthwhile for many applications. So I'll take a couple brief questions on this stuff and then talk about future work.
Do you have any data on the accuracy?
Yeah.
Or the extra bandwidth that's required with this?
I think I have both. So I can tell you, let's see, where do I have accuracy? Let's look at it in this graph here. So what you're looking at here are graphs. So this is graphs of kind of 2 versions of this technique. The naive one where we just kind of fetch every single time we do a lookup and an address finds a possible stream, we'll fetch. That's the first bar. The second bar is where we're doing this approach that I mentioned before of trying to compare the previous 2 occurrences. Okay. The bottom portion underneath 100% here is, again, the coverage number. So what fraction of the misses do we eliminate? The top portion shows you how many extra blocks were brought into this buffer on the chip and then thrown away. So you can see without this end-of-stream prediction technique, it's really bad, right? Because we're going to go nuts fetching several times what we actually successfully eliminated. However, once you put that technique in fact, the erroneous fetches are smaller than the useful fetches. And so we're wasting about twice as much bandwidth. So the bandwidth cost here in terms of these discards is proportional to kind of the amount of benefit we got. You also have a bandwidth increase because the program's gotten faster, right? So, but this cost is certainly still worthwhile. And
double your memory overhead for the directory because now you have to keep 2 pointers.
That's correct. That's correct.
So end of stream prediction, you look at the last 2 instances of the head
Correct.
block and compare them.
That's correct. And so that actually further increases the directory overhead, and also further increases the cost of moving address sequences around. So it's getting even more bandwidth expensive than that, but it comes out as a net win because of this huge reduction in the amount of data that you stop moving. So let's jump back then. Oh,
More question. Do you apply this to the addresses that remain read-only? In the sense that I read it, but I came back and wrote to it as well?
Yes, but that's actually a small, so in these, we are addressing kind of all of the off-chip misses, but the dominant portion here are communication misses. So 3/4 of what is in these results is, in fact, cache-to-cache transfer type misses, or misses where there was a writer by someone else, so you wouldn't have been able to get it if you made your caches larger. Whereas 1/4 of it is, capacity issues, which could be read-only or read-write. We're only going after the read misses, though. Right.
Okay. The reason I'm asking is that if a good chunk of those are actually writable addresses, and it's very unlikely that they will be written, by actually trying to retrieve them earlier into your cache, you are incurring an additional traffic in the system.
Right. So in fact, you're going to need to do a permission upgrade. If the first access is a write, then then that was bad. You made more traffic. If it was a read and then a write, then again the baseline system would have done a read miss and then a write miss potentially, and these kinds of things. Now, again, the key idea here is to go after the right problem and try to fix that. So there's migratory sharing optimizations that can tell you, which we didn't combine with this, but in principle you could, which would say, look, always move this thing around with write permission. And secondly, there's a lot of work on how do you avoid ever waiting for writes in a multiprocessor, and we can talk more about that. That's actually, I'll briefly mention it later in the future work here. So let's take now 5 minutes or so and discuss some of where I'd like to go moving forward. So let's see. So let's begin with this. Forward here. Okay. So I think this is an observation that's not going to surprise anybody in this room, considering that Microsoft has decided that they want computer architects. So this is the data that I showed you at the start of the talk, and there's really two regions in this graph. There's this clock and ILP era, where processors were increasing at 50% a year, and then we can argue over the exact date, but I'll claim, at least Tennessee and Patterson claim in 2002, there's this knee in the curve, where clock speeds have stopped advancing, and because of verification constraints, we haven't been able to make microarchitectures that continue to get ILP, and so now we're getting, well, they claim 20% a year, and that's what the data has shown up to now, but we can argue about whether we're even going to get 20%. So we still need to sell chips and operating systems and other wonderful applications, and so these big companies have kind of bet the farm that if they give us more cores, we'll somehow manage to be able to find ways that people will still want to buy chips in the future. And so now we as system designers are faced with this challenge. How do we program, evaluate, and design in this context where we're getting cores instead of raw clock speed? So I'm going to talk about just three slides here about the challenges that I see that interest me in this area. So the first one is this parallel programming wall. So there is parallel software today, but there's very limited domains in which we bother to parallelize because, parallelism is hard to extract. There are these really complicated programming models for how we write parallel code, and there are new sources of bugs that don't exist in sequential programs. And so, my claim is that identifying parallelism is hard. Can we do something to get rid of all these other concerns and make it so that the programmer's only task is to, in fact, identify the parallelism in some algorithm? Okay? So I'd like to zoom in on one of these challenges, this difficult programming models challenge. So if you look at shared memory systems today, programmers really have to choose between two flavors of system. On the one hand, there's systems which give a strict ordering of memory. So memory allows one access at a time from programs, and all of the memory accesses from a particular program appear to occur in order. And this is intuitive because it behaves like a multitasking operating system, right? Programmers are aware of the idea that another task might come along and switch out with you and then access memory for a while, and then you might get switched back in. But it prohibits all sorts of parallelism in the hardware. Okay? Whereas on the other end of the spectrum, we have these hardware systems which allow all sorts of parallelism, so memory access can go out of order, and yet now the programmer needs to indicate where ordering is necessary. So for example, acquire the lock first, then play with the shared data structure. Okay? So, you have this choice now, either simplified programming model or high performance. Can we have our cake and eat it too? Of course, I wouldn't pose the question if the answer weren't yes. That's exactly right. This is, in fact, very closely related to what the work both of us have actually back-to-back papers in ISCA 2007 this year. So since you guys are already familiar with this, again, the same basic idea. Instead of enforcing ordering over individual accesses, we enforce order over coarse-grained sequences. There are some differences in how we approach things. So we're not using this hash-based coherent stuff that he talked about. But in the end, the outcome is that you can get strictly ordered memory models, or you can choose a memory model and hide all of the latency that you incurred on stores. But there are further questions. I think this is not the end of the road. This is one small challenge among many that face the parallel programmer. Can we, for example, get rid of synchronization penalties? Or can we throw hardware at the problem of aiding programmers in debugging, right? Or finding performance bottlenecks because there's some new queue in the 8-core system that wasn't in the 4-core system. So second challenge that we already talked about a little bit is this evaluation challenge, right? This shows you how slow microarchitecture simulators are relative to actual hardware. We can't run applications to the end. So the approach that we've taken is to try to use statistics, so sampling, to solve this measurement problem, right? Question?
The chart had 2 years. If you get enough people at Microsoft to donate their machines on screen server time, you may be able to get 2.5 CPU years in a semi-decent amount of time.
That implies that we can parallelize things, right? So how do you parallelize the detailed simulator? That's a very difficult problem. And instead of parallelizing the detailed simulator, what we do with the sampling approach is make it so that, in fact, all of these measurements can be independent, right? And that's where we're getting this 1000x parallelism, right? If we have 1000 measurement locations, we can farm that out over the giant number of machines that are available here to drastically reduce that turnaround. But again, we've only figured this out for certain classes of applications, and we haven't really thought about what does this picture look like when we get to a really large number, of course, like 1000 CPUs. So that's very interesting. And then the last thing that I'd like to touch on, and then I'll open it up for any questions you might have, that excites me, it'll be interesting to find out whether this excites Microsoft or not, is kind of what I call the architectural opportunities of disruptive technology. So what do I mean here? It's new manufacturing tricks that have kind of come down the pipeline or appear to be happening soon that fundamentally alter assumptions that we take for granted in the way we design the computer system today. So 2 examples that I see that a lot of people, now more people are betting will happen than not at this point, are 3D die stacking and optical transceivers on silicon. So what 3D die stacking is the ability to actually put various layers of a chip together in a 3D stack, potentially even with different manufacturing technology. So you could have a processor with DRAM on top of it, drastically increase your cache size. Or we could imagine instead going to Intel and buying slices of a processor that are put together. How would we redesign the system with that capability, right? And I could 2 slices of floating point and 6 slices of cache and give me a sensor on top, right?
Get the heat out.
So there are some issues there, right? There issues are things like power dissipation. How do you actually do the alignment? The alignment's actually harder. So people claim that the heat can be dealt with. You have to put giant metal conductors through this thing that just pipe heat out. It's like heat pipes through the chip. But people claim that those problems can be solved. So I'm not an expert in the manufacturing, but suppose we get it. What could we do, right? Same with optics on chip, right? 100 times the bandwidth per unit area on the chip, or capabilities like broadcast over the entire chip, right? What would you do if you had 1,000 cores which had a cheap broadcast? How would we redesign software and hardware? So those are the kinds of things that that I like to think about. So that's everything that I have. Thank you guys for your attention, and I welcome questions on the talk or any of these other random ideas that I talk about here at the end. What's that?
I have you in a couple hours. I can ask you that.
Okay. Anybody else with questions, concerns, complaints, tomatoes to throw?
In terms of your presentation, one of the first examples that you gave about the patterns in database pages, you didn't raise it at that point, but it's a little misleading because the same pattern is not that likely other than the header and the slot array at the end of the page to follow exactly the same record distribution pattern across different pages is not very likely.
Depends on whether the pages are variable size, the records are variable size, right? I mean, variable size records, then the question is there any kind of repetitiveness in the lengths that would kind of...
All I'm saying is that you can find much better examples in metadata space without going into the pages. That's just feedback for you because
fair enough.
Whenever a database person looks at it, it's like,
maybe not.
A little.
So it turns out...
a little BS-ish when it just look at that.
Fine.
Even though there may be a lot of truth to what you're saying,
right.
It raises a little more concern.
Sure, so fair enough. I mean, one of the things that we have seen in terms of looking at the spatial, so that's my colleague's thesis versus the temporal stuff, turns out that going after sequences is really the right thing to do for things like online transaction processing, where there are a lot of locks and thread scheduling initiation and so on. And the spatial stuff is really more effective for DSS style stuff, or data mining type things. So they looked at TPC-CH there, and in some queries we actually get something like 75 or 80% of the misses based on just walking over one giant table with a repetitive enough pattern that, in fact, you get the same thing over and over. And there's some alignment issues. There's some games you can play in the hardware to deal with alignments as long as the relative offsets repeat.
And another potential area for you to maybe think about, but that requires you to capture patterns in virtual addresses, is to understand that the patterns actually do repeat themselves at different virtual addresses.
Right.
But that are kind of multiples of each other or something like that.
In the spatial memory streaming stuff, we do that.
Stuff like that. I bet they try to do something like that. But
exactly.
How do your approach and his or her approach work together?
Yeah.
What does it mean to have both the spatial and the temporal one in the same thing? Because your design seems like it's
just
the temporal one. I bet she will require a whole bunch of other things for the spectral one. What does
in fact,
have?
It's a very interesting question, and there's still an ongoing project at Carnegie Mellon that is looking at this. Because so the distinction here, so temporal, as we've said here, is fundamentally an address correlated based thing, right? Address A tells me what the traversal is. With the spatial, what we were doing exactly what you say. You learn a pattern that applies over many distinct addresses. So it's actually fundamentally a code correlated thing. You learn that this PC, when it accesses a region of memory, suggests a layout of other nearby things that will be accessed. So one is code correlated, the other is address correlated, so it's kind of hard to, how does the lookup mechanism combine? So the vision is that you'd want kind of sequences of little algorithms that generate the local, like patterns, or a sequence of patterns that tells us what the entire traversal is. Because it's much more efficient to encode things in terms of like an algorithm or a bit mask that generates the spatially related stuff. And yet you still want the temporal stuff to get these pointer sequences. But we haven't yet figured out how to combine these things because of the differences in the way the lookup works. What we do know is in terms of opportunity, if you look at the Venn diagram of how they overlap, the overlap is actually small. So the overlap is about the same size as what each technique individually gets by itself, even within each of the workload classes. So even though, the spatial stuff is better for DSS, the temporal stuff is better for OLTP, put them together, you'll do better, even better on each of the workloads once we figure out the hardware. Okay. Well, thanks a lot.
Thank you.